Welcome to another explainer where we treat your exam time like absolute currency. We are calling this session the trading floor because when you walk into that exam hall, every single minute you spend writing is an investment. You need to be making split-second decisions to invest your time where the marks are highest. Today, we're diving deep into Cambridge Computer Science exam strategy. And look, whether you are sitting syllabus 0417, 0478, 0983, 0984, 2210, or especially the AS and A-Level 9618, the rules of the trading floor apply to you. We are specifically looking at data verification during data transfer with a laser focus on byte and block parity checks. Now, right off the bat, I want you to picture two very different types of students. First, there's Alex. Now, Alex overloads his answers with raw computer science facts. He's just dumping everything he knows onto the page, writing literal essays, but providing zero actual analysis of the question. Then you have Sam. Sam is the complete opposite. Sam rushes through the paper, trying to beat the clock, completely missing the command word requirements and losing massive points on tiny technicalities. Throughout this explainer, we are going to look at exactly why both Alex and Sam are leaving a fortune of marks on the table, and more importantly, how you can guarantee you don't make their exact same mistakes.
Okay, so let's dive into this really high-stakes question. Why do multi-step calculations absolutely destroy student averages? Because principal examiners repeatedly report year after year that data verification during data transfer is one of the most misunderstood areas where students just go bankrupt on marks. Let me paint a picture for you. You are given a block of data on your exam paper. Let's say it's 8 bytes of binary transmitted with a 9th parity byte at the bottom. You are asked to find the transmission error. This is a classic multi-step calculation. Now, students like our friend Sam, they try to jump straight to the final answer. They visually scan the binary, they guess the flipped bit, they scribble down row 3, column 4, and they immediately move on to the next page. But here's the critical secret. Cambridge examiners aren't just looking for a coordinate. They don't care that you can play battleship with binary numbers. They're assessing your computational thinking process. When you skip the logical steps of explicitly verifying the row parity and then explaining how you cross-referenced it with the column parity block, you forfeit the majority of the marks. Even if your final answer happens to be 100% correct, you are essentially doing all of the mental heavy lifting, but you are flat out refusing to collect your paycheck. It's crazy.
So, here is our blueprint for today's session. First, we'll uncover the parity check trap. Second, we'll break down the method mark strategy. Third, we'll explore core algorithmic thinking. Fourth, we'll expose the top 3 examiner warnings. And finally, we'll wrap up with the ultimate system: deconstruct, solve, evaluate.
Let's move right into Section 1 and see how this builds our foundational understanding of the biggest trap on the exam paper.
So the absolutely crucial point here is that examiners demand logical, structured reasoning. The academic benchmarks across all these Cambridge syllabuses prioritize analytical depth over superficial breadth. Now, this is exactly where our other student, Alex, goes completely wrong. Alex sees a question about parity and proceeds to write a massive half-page paragraph defining what even parity is, what odd parity means, maybe throwing in some history of data transmission for good measure, but he completely fails to actually apply that knowledge to the specific data block provided in the question. Listen carefully. Examiners do not want a dictionary definition from you. They want a demonstration of skill. You really need to understand that the assessment objectives are heavily weighted towards applying your knowledge in a specific context. If you just state facts without analyzing the specific binary blocks sitting right in front of you on the page, your mark potential drops to 0. You've wasted your time investment.
Now, what's really interesting here is understanding that verification isn't just some simple math trick. It is a full analytical framework. A parity check, and specifically a block parity check, is a genuinely ingenious concept. Think about it. You have individual bytes of data, and each one has its own parity bit appended to it. That is your horizontal check. But then an entire additional byte is transmitted at the very end of the block. This acts as a vertical parity check for every single column of bits. When an error occurs during data transfer, you have to use systematic analysis to find the exact intersection of the failing row and the failing column. And here is where you secure the bag. You must provide evidence-based reasoning. You can't just write bit 5 is wrong. No way. You have to state something like byte number 4 has an incorrect even parity count of exactly 3 ones. Furthermore, column 5 in the parity block also fails the even parity check. Therefore, the intersection of byte 4 and column 5 pinpoints the erroneous bit. Do you see the difference? That is how you demonstrate a true analytical framework to the examiner.
Let's transition to our second concept, which is where you actually invest your time to get the absolute highest returns on your exam paper. But before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay,
Let's get into your ultimate high-stakes exam strategy. You must pivot your entire focus away from just getting the right answer and towards securing these critical process marks. We call this the method mark strategy. Have you ever heard of the PEAL framework used in analytical writing? Point, evidence, explanation, link. Well, guess what? Top computer science students structure their answers the exact same way. If the command word on the paper is explain how the error was found, you start by making your point. The error is located in bit 3 of byte 2. Then, you provide your evidence. The sum of ones in byte 2 is an odd number, which violates the agreed even parity protocol. Next, you add the explanation. The parity byte transmitted at the end of the block also shows an error in column 3. And finally, you link it all back together. Therefore, the intersection of this row and column identifies the exact bit that was flipped during transmission. I'm telling you, if you want to spot a top-tier candidate's exam paper, look for that PEAL structure. It is the absolute best way to ensure every single method mark is captured. If you try to write this any other way, you are playing a very dangerous game with your grade.
And this brings us to the procedural sequence you must follow when tackling parity check questions. This is how we take a flawed answer and transform it into a green checkmark masterpiece. Step 1. Deconstruct the question's command word. Is the examiner asking you to identify, describe, or explain? Those require totally different depths of answers. Step 2. Extract the relevant data. Literally isolate the specific binary block on the page. Step 3. Select your analytical framework. Are we using odd parity or even parity here? Don't mix them up. Step 4. Execute with clear notation. I highly recommend you physically circle the erroneous row and column on your exam paper. Show you're working out. Make the examiner see your thought process. And step 5, present your answer with correct terminology. Please do not write the 1 turned into a 0. It sounds so unprofessional. Write a bit was flipped during data transfer, causing the parity check to fail. By explicitly showing this exact sequence, you transform a risky, rushed answer like Sam's into a guaranteed full mark response.
We are moving right along to the third phase. Let's look at how core algorithmic thinking actually looks on the exam paper.
Okay, you need to understand that algorithmic thinking isn't just reserved for the programming sections of your paper. It applies directly to how you solve these data verification problems. Step-by-step decomposition means breaking down a block of binary data systematically, row by row, column by column. It's essentially a while loop you are running in your own head. I want you to imagine a 60-second visual countdown timer right now. If I put a complex binary table in front of you, you need to be able to scan that data instantly, like a machine. You decompose the problem. You check row 1, pass. Row 2, pass. Row 3, fail. Okay, pause the row loop. Now switch to the vertical column loop. Column 1, pass. Column 2, fail. Boom, you found the intersection. That mental algorithm, that incredibly systematic approach, is exactly what Cambridge is testing you on. You are selecting the appropriate mental data structure to solve a multi-layered problem as efficiently as possible before that timer runs out.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get back into it. Top-scoring candidates don't just write code. They demonstrate what we call evaluative thinking by hitting these 4 exact criteria on the screen. Let's apply this. Why would a network use a parity block instead of just a simple parity byte? You must be able to analyze the trade-off. A single parity byte is fine for detecting if an odd number of bits flipped during a single transmission, but it has a massive limitation. It cannot pinpoint exactly which bit flipped, and it completely fails if an even number of bits flipped, right? Now, a parity block introduces a new limitation. It takes up more bandwidth to send an entire extra byte across the network. But what's the trade-off? The trade-off is the incredibly powerful ability to actually correct a single-bit error by finding that exact intersection. Justifying these network decisions with concrete evidence is how you push your score into those absolute top-grade boundaries.
Now let's open up the Principal Examiner's Playbook to see exactly where students are losing their marks. Welcome to the interactive workshop part of our session.
So the absolutely crucial point is right here. If you fail to check boundary conditions or miss an edge case, you immediately lose the easy marks. Let's do a quick challenge. I want you to act as the examiner and find the flaw. Imagine a student writes this sentence on their paper. Parity checks guarantee that data is transmitted without any errors. Did you catch the flaw? I'll give you a second. The word guarantee is completely 100% wrong. This brings us directly to warning number 1 and 2 from the examiners. Edge cases. What happens if two bits flip in the exact same byte during transmission? Think about it. The parity might actually remain even, and the error goes completely undetected. This is a massive edge case in data verification. Parity checks do not guarantee data integrity. They only verify it up to a certain mathematical boundary. If you don't explicitly state the limitations of a parity block in your exam, you are basically waving a flag to the examiner signaling that you don't actually understand the underlying mathematical mechanism works.
And this brilliantly illustrates another classic mistake: providing a generic textbook explanation instead of actively linking your answer to the specific scenario provided. Let's do a 30-second speed writing challenge conceptually. Let's say the exam question is about a bank transmitting secure financial records using odd parity. A generic answer, the kind Alex might write, says, parity checks find flipped bits, 0 marks. But a context-specific, Peel-structured answer says, if the bank's financial transaction data suffers a flipped bit during transfer, the odd parity block will detect the error, allowing the system to request a retransmission before corrupting the customer's account balance. Do you see the massive difference there? You must tie the technical concept back to the bank, the financial records, or whatever scenario the examiner has handed you. If you don't use the vocabulary from the prompt, you are writing a generic answer and Cambridge will heavily penalize you for it.
Finally, let's look at the ultimate repeatable mental model to guarantee your success in any data interpretation question.
This is your ultimate cheat sheet recap. It is a 3-rule system that guarantees top marks if you follow it. Rule 1. Deconstruct. You have to decode the command words and identify the given information. Is the system using odd or even parity? How many bytes are in the block? Don't assume, read it. Rule 2. Solve. You break it into logical steps using that PO framework. Find the row error, find the column error, pinpoint the intersection systematically. And Rule 3. Evaluate. Manage your time matrix, check the reasonableness of your answer, and justify your recommendations. Let's say the question asks you to find a single flip bit, but when you do the math, your row and column intersections don't line up at all. Your evaluation step should trigger a massive red flag in your brain. You must check the reasonableness of your working out before you dare move on to the next page of the test booklet.
Now, what's really interesting about this slide is a quick memory hack. I want you to turn your parity checks into a visual story to help encode the process for those high-stress exam moments. Imagine the data block as a literal grid of city streets. The rows are the avenues, the columns are the streets. A flipped bit is a broken traffic light causing a jam. The horizontal parity check, that's a police car driving down the avenue and noticing a problem. But the police car doesn't know exactly which cross street the broken light is on. The vertical parity block, that is a police helicopter flying straight down the street from above. Only when the helicopter and the police car cross paths at the exact same intersection can they pinpoint that broken traffic light. By encoding these concepts visually, your brain can instantly retrieve the systematic methodology of byte and block parity, even when the exam clock is ticking down and the pressure is on. Listen, students who implement these computer science strategies see an average improvement of 2 full grade boundaries. But that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE, to excel in your Cambridge examinations. Subscribe right now to @acexams_IGCSE and click that bell. Don't let another exam pass you by.
I want to leave you with this final, high-stakes question to think about. How will you apply this framework on your next exam? Remember, in computer science, parity checks remind us that catching a mistake isn't just about spotting an error. It's about having the systemic framework in place to prove exactly where things went wrong. The next time you look at a grid of data, ask yourself, are you just guessing like Sam, overcomplicating it like Alex, or are you executing an algorithm like a top-tier candidate? Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.